Alright, so we're going to do things a little bit more different this time. Instead of me doing a lot of lecturing, I thought that I would take this video to just go over and look at a few problems in Boolean algebra. So this is part 2 of Boolean algebra. In this video, what we're going to do is we're going to look at more properties of Boolean algebra, such as other redundancies and the consensus theorem. You will notice that in Boolean algebra, you will be asked to factor or multiply equations into two different forms. The first form and most commonly used is called the sum of products, and that is exactly what it means. It is a series of AND gates being ORed together. The second form is known as the product of sums, which is just the opposite, a series of OR gates being ANDed together. In future videos, when we look at stuff like Carnot maps or minterm and maxterm expressions, I'll show how both forms of these equations can be used to solve or map out variables so that you can simplify these equations. But for now, let's take a look at equations that can be simplified simply by taking the equations that we have taken in the previous video and just building them up together. So we're going to look at that now, and we will start with some of the redundancies that we did in our last video. So in the last video, this is one of the problems that we looked at. We looked at x ORed with xy or x plus xy, whichever way you prefer. And we said that the answer was x because xy is a redundancy. And we can prove this by using the distributive property, like so. So we take x and then we factor out the x, and we have 1 plus y, which turns out to be 1 plus y is equal to 1. So x times 1, or x ANDed with 1, makes x. Another redundancy that we looked at was this one, in which the redundancy was the y variable itself, because we are taking the x ANDed with y naught, and we are ORing it with the term xy. Since we are ORing both sides of the variable y, that is y naught and y, in the x variable, the answer to this equation is x, and we can prove this by factoring out x with the distributive property again. And it shows that y naught plus y turns out to be 1, and x ANDed with 1 just equals x. Enough factoring out. Let's use the distributive property now to simplify this equation. We have x ANDed with x plus y. Well, if we use the distributive property, we know that x ANDed with x is xx, and x ANDed with y gives us the term xy. X and x is simply x, and since we already did the equation for x plus xy in a previous problem, we know the answer is x. Alright, how about an equation that is a little bit tougher? Let's take a look at x plus y times x plus y naught. Well, for this one, if you know your algebra, you know that with polynomials, we should multiply them using the FOIL technique. FOIL stands for first, outer, inner, and last. That means you take the first terms first and multiply them. Then you take the outer terms and multiply them. Then you take the inner terms and multiply them. And then you take the last terms and multiply them. Then you add them all up. So x times x turns out to be xx. Then we'll do the outer, x times y naught, which is xy naught. Then we do the inner, which is xy. And then we do the last terms, which is y naught. After that, we start simplifying. We know that x ANDed with x turns out to be x. And we know that y ANDed with y naught is a contradiction and turns out to be 0. This leaves us with the equation x plus xy naught plus xy plus 0. Then what we do is take the xy naught plus xy that we have done in a previous problem, and we just simplify that to x, because we know that xy naught plus xy is x from that previous problem. So now we're left with x plus 0, which turns out to be x. Let's try another equation using the distributive property. Let's look at x plus y naught ANDed with y. Well, let's just go ahead and multiply y into our equation inside, just like we do with the distributive property. And what we have is xy plus y naught. Well, we know that y ended with y naught is a contradiction, so that becomes 0. And what is xy plus 0? Well, anything plus 0 is equal to itself. So the answer is xy. Now let's look at this equation, which is xy naught plus y. In this one, what we are going to do is we're going to take the xy naught term and we're going to factor it out. So we are going to factor this out into two product of sums terms. So we're going to take the y and we're going to OR it with x, and then we're going to OR it with the second term, which is y naught, and we have x plus y times y naught plus y. Well, we just know that y naught plus y turns out to be 1. And what is x plus y ANDed with 1? Well, anything ANDed with 1 is just equal to itself, so the answer is x plus y. The y naught, in this case, being redundant. Let's try something a little harder and add a third variable into the equation. So let's take a look at x plus y ANDed with x naught plus z. For this one, we are going to use the FOIL technique. So we are going to combine the first terms, x naught, combine the outer terms, xz, combine the inner terms, x naught y, and then combine the last terms, yz. We know that x ANDed with x naught is a contradiction and turns out to be 0, so we can eliminate that. And we are left with the equation xz plus x naught y plus yz. I'm going to stop here because, believe it or not, we can, in fact, eliminate one more term from this equation. It turns out that the yz is redundant. Why is the yz redundant? Well, this is a phenomenon that is known as the consensus theorem. In the consensus theorem, when a variable appears in one term, in this case xy, and the complement of that variable appears in another, in this case x naught z, a consensus term is formed by multiplying the two terms, that is, without that particular variable, together. In this case, we take out the x and we combine the two terms together, which turns out to be yz. And this works as well for and OR gates. So in this case, x plus y ANDed with x naught plus z, ANDed with y plus z, we just take out the y plus z because y plus z is redundant. And the answer turns out to be xz plus x naught y. A handy tip when using the consensus theorem, all you have to do is just find the variable that is complemented, in this case it was x naught, and find the term that does not contain this variable. And that turned out to be the redundant term. Now we're going to do a couple more problems. Let's take a look at another one, a little bit more complicated problem with multiple variables. Here we have twxy plus vwxy plus wxyz. If we use the distributive property, we know that what we have, these terms in common, is the term wxy. So we just factor out the wxy, like so, and then we are left with the terms t plus v plus z. We're going to look at more of these equations a little bit later on, and we're going to also look at sum of product to product of sum and product of sum to sum of product conversions when we move on to the third part of Boolean algebra. So anyways, thank you for watching this second part. I know it was mostly problems, and it's a little bit different from the other videos that I did because I lectured a lot in those videos, and in this one I just threw problems at you. Go ahead and comment if you want whether you prefer the lecture style or the problem style, and I will try to lean more towards that in future videos as well as future courses. What we're going to do next is we're going to look at sum of product to product of sum conversions and the other way around. We're also going to look at more complicated problems in Boolean algebra and focus more on the consensus theorem. So please thumbs up, comment, and subscribe, and I hope to see you next time.